Joint work with my colleagues Matthew Salzman and Nick Barnes, and this work is about semantic segmentation, and basically it means giving us a meaning to every pixel, a label to every pixel in an image. Common approaches for semantic segmentation are mainly supervised, and that means that you have a classifier, and on top of that you put a CRF that will give some consistency. The classifier gives you a probability per pixel, and then a CRF will give you some consistency over the whole image. In the last year, there has been some work on efficient inference on the CRF side, and we have seen that if you have a local neighborhood, you will improve over unitaries, and then if you, instead of a local neighborhood, you consider all the pixels in the image, you will have even an improvement over the local CRF. Lately, we have also seen that if at test time during the inference you consider more than one image, all the images that you want to test jointly, what you will see is that you obtain even larger improvement over unary, using only the unitaries. So the main limitations of this approach are, first, that they are based on a classifier, so it means that you have, every time you have new data, you have to retrain your classifier or you have to discard that data. The second is that the inference now is taking care of all the test data available, but is forgetting all the training data, so you are not really using all the data that you have available. And now that you have efficient inference algorithms, the problem is that the computational cost, the bottleneck, is moved to the classifier. So the main time-consuming part is computing the unitaries. So what we propose is based on transductive algorithm. And the idea behind transductive algorithms is these algorithms are in the family of semi-supervised approaches, and that means that they can handle labeled and unlabeled data. And this specifically, transductive means that part of the unlabeled data is the test set. So you will build your model at the same time when all the test data is available. One of the limitations of current approaches is the scalability. The current state of the art is giving you results for up to a few thousand nodes. So the question is, well, what happens with these larger scale data sets? Our approach basically constructs a fully connected graph over all the data available that you have, labeled, unlabeled, test, training, whatever you have, you put it in a fully connected graph. And then you formulate the semantic segmentation quite similar to a fully connected 10 CRF, with the particularity that you will not have unitaries in the formulation. Then if you modify, with a slight modification to the classic or to the last efficient inference method, you will see that this is still efficient. One of the advantages of our method is that this formulation allows the inclusion of new data available, and this new data can become as a labeled data or as a sparse unitaries if you have time to compute some, to run a classifier in some of the data points. Our results show that if you have enough data, you will get competitive results even without computing any single unitary, and that means that the computational cost is going to go is going to be reduced significantly. Then we can also see that as soon as you can add more and more unitaries in a sparse manner, but the more unitaries you add, the better classification accuracy you will get. So in summary, we can see that the advantages of our method is, first, the scalability. We can run up to 1 million nodes in a standard desktop. The computational cost, depending on the limitation of your accuracy, is going to be reduced significantly. Then also our approach allows the inclusion of new data if it becomes available, and more importantly, each test data is going to take advantage of the full data set, including training and test data.